Welcome back. So in this session, we are going to discuss about argument and modulus of a complex number and see how we can define those two concepts with respect to different quadrants of the Argand diagram, which will help us to do the transformation of any complex number to either exponential form or polar form. And once you understand how to find the polar form and exponential form of a complex number, you will be in a position to carry out more other operations when later on we'll be describing how to find roots and end roots of complex numbers by application of the de Moivre's theorem. So begin by first discussing how to express a complex number into polar form. And before we do that one, we'll begin by first explaining or defining what modulus and argument of a complex number means. So to appreciate or to be in a position to define these two terms, I want us to consider a complex number. So consider the complex number z equals to x plus yi on the Argand diagram as shown below. So let this be the imaginary axis. Let this be the real axis. So this is the imaginary axis. And then let Z be at this point. So let this be where we have our Z number. Then I can define so let this point be P, and let this be our usual origin O. And if this way we have our number Z, then you know that if you are to extend this number on the, so this will have IY or YI. So which means that in this right angle triangle, make this angle to be theta. So this will be Y units, and then this base will be X. And this, let's call this hypotenuse rectangle triangle formed here. Let's call it R. So note that given a complex number, Z given by X plus IY, we define its modulus or length, or it's also called magnitude, or sometimes it's also called absolute, by, so we write this, which is the square root of x squared plus y squared. And this is taken to be the positive square root. So that's how we find the magnitude or modulus of the complex number z, where we only pick the positive square root. So in general, this what we'll be calling R. So it'll be the length you're calling R here is what is the same as absolute value of Z. Where you'll be seeing R in this discussion, in this chapter, it will mean the magnitude or modulus of Z. And so once we have that, in this right angle triangle from Oshachota, we can define other trigonometric ratios. So from Oshachota, we know that now Oshachota is simply an acronym to help us remember the trigonometric ratios in a right angle triangle, where this letter S means sine is opposite over hypotenuse. And then this C means cosine is what is before cosine is A, so adjacent over hypotenuse. And this T means tan is opposite over adjacent. So that's simply what the acronym Oshachota means. Now, from this triangle, we see that we know the complex number is x plus iy. So this angle theta here, we can say tan theta, tan given by opposite, which is y, over adjacent, which is x. So that theta alone can be given by tan inverse of y over x. So that is how we find the angle theta. And then this angle theta has a special name. So the angle theta between the radius vector OP and the positive real axis is called the argument of Z. And it's usually measured in the anti-clockwise direction from the real axis and has infinitely many values. But we usually, when denoted by so this is actually how we denote that angle arg Z, so means argument of Z. So when argument of Z is restricted from minus pi to pi, the same thing as saying from minus 180 degrees to positive 180 degrees, we call it the principal value of the argument. So we call it the principal value of the argument. Now, so when so there are 4 different cases to consider. So cases to consider in the interpretation of argument of Z. So case 1, when Z is in this quadrant, so when Z is in this quadrant, so theta will be here. So as usual, this is Y, and then this is X. So it means that now tan theta will be given by Y over X. So which means theta is tan inverse of Y over X. So that argument of Z will be the same as the value of theta, which will be the same as the value of tan inverse of Y over Z. And then the magnitude of Z remains to be X squared plus Y squared. Then we can give an example to illustrate this. Find the magnitude or modulus and argument of Z equals to 2 plus 7i. So solution, the first thing that you need to know is to represent the sketch of that number in an Argand diagram, and know that 2 plus 7i will be a number in this quadrant. So this is where you have our theta. So this will be 7 units. This will be 2 units. So that you say magnitude of Z will be square root of 2 squared plus 7 squared, which is square root of 4 plus 49, which is root 53. Then this angle being in this first quadrant, then it's very direct that argument of Z is the same as angle theta, which is tan inverse of Y, which is 7, X, which is 2. And tan inverse of 7 over 2 is given by 74.05 degrees. So this will get 74.05 degrees, or if you like, you say, divide that one by 180, you'll say 0.4114 pi radians. So this becomes our argument of Z for that given complex number. Then case 2, if you have this as your complex plane, and the number is in this quadrant, Z is here. What we normally do, remember that argument of Z is measured from positive real axis to where the angle is formed in this plane. So you call this one, so remember this remains to be your Y, you'll have X units here. So call this one alpha. So tan alpha will be given by opposite, which is Y, over adjacent, which is X, which means alpha will be given by tan inverse of Y over X. So once you get this one, then argument of Z becomes, remember this total alpha plus this angle here should give us 180 degrees. So it will be the same as 180 degrees minus alpha, or you say pi minus alpha. So we can demonstrate with an example. For example, if we have a number Z given by -4 plus 3i. So here, if you are to get modulus of Z, it would be square root of -4 squared plus 3 squared. So this will give us square root of 16 plus 9, and this turns out to be 5. Then to get the argument of this number, the first thing is that you need to sketch. And when you sketch, you realize that you'll have this number will be in this quadrant, whereby along the X, we have 4 units to the left. Along the Y, we have 3 units on the Y-axis. So this way I'll put this Z. And then you mark this one to be alpha. So in the right angle triangle, you can always find alpha, because tan alpha is opposite 3 units over adjacent, which is 4 units. So which means alpha will be the same as tan inverse of 3 over 4 equals, so 3 divided by 4, then tan inverse of that answer will give you 36.87 degrees, which you can convert in pi radians by dividing by 180, so which is the same as 0.2048 pi. Now, the required argument is this angle, not the alpha, but this angle measured from the positive real axis. So the argument in this case becomes 180 degrees minus 36.87 degrees, or you say pi minus 0.2048 pi. So 180 minus 36.87 will give you 143.13 degrees. Or if you are using pi radians, we'll have 1 pi minus 0.2048, and this will give you 0.20 79525. So note that whenever we are dealing with trigonometric functions, pi radians, we usually write pi to mean it's actually this pi radians. So we don't, like in high school, we used to write pi power c. We usually don't put that power c, but we understand it's there. That's an answer. So just write pi, and the interpretation is the same way you know that it means pi radians. Then, so know that the key thing that in what you are doing the discussion here is that if you are given a complex number to express or to find its argument, you must always sketch to know where the complex number lies. And because the argument is measured with respect to the positive real axis, then you must always remember that. And when you say principal argument, then it means that it should be a number between minus 180 degrees and positive 180 degrees. So case 3, you can have your, if this is your complex plane, your z can be here. So that if this is where I have my z, you define a right angle triangle here. So you call this one alpha. Then if you restrict yourself that you want to make argument to be between minus pi to pi, so what is so called, then it means that now you will actually be interested in this angle here. So this is what you'll call the principal argument. So that this will remains to be your y, this remains to be your x, and so tan alpha remains to be y over x, so which means alpha is the same as tan inverse of y over x. So the principal argument will be given by, remember when I add all this one, I'll be negative of pi minus alpha. Because I know that all this will give me pi or give me 180 degrees, all these angles on a straight line. But remember now I already have this alpha, so the remaining part will be simply 180 minus this value of alpha. But because I'm measuring the negative direction, remember when this is the positive direction, while this other one is the negative direction. So that's why I have a minus sign here. So for example, if you are dealing with the complex number z given by minus 2 minus 3i, then what you do is you sketch this number in the Argand diagram, and this number will be this. So call this one alpha, along the x is 2, along the y is 3. So then I will say alpha, tan alpha is opposite 3 units over adjacent, which is 2 units. So which means alpha alone will be tan inverse of 3 over 2. So 3 divided by 2, then tan inverse of that answer is 56. It will give us 56.31 degrees. Or when you divide this one by 180, 56.31 divide 180 will give us 0.3128 pi radians. So which means then that the required argument, the principal argument will be this angle here. And because it's measured in the opposite direction, what argument is, then you'll have a negative sign. So argument will be the same as minus 180 degrees minus 56.31 degrees. So 180 minus 56.31 be 123.69 degrees, or you can say pi minus 0.3128 pi. If you want to put your angle in pi, then you have 0.6872 pi radians. But all these have negative, this negative, because we're measuring in the opposite direction. So we'll have argument, the principal argument will be minus 123.69 degrees or minus 0.6872 pi. And please note that if you are to keep the angle to be positive, then remember you'll be interested in this size of this angle here. So know that this one now will be the same as 180 degrees plus 56.31 degrees. So 180 plus 56.31, so 236.31 degrees. Please note that if you define the tangent of this angle here and the tangent of this negative 123.69, you actually get the same value. The only difference is the reason that's why we are saying that when you want to restrict your argument to be from minus 180 to 180, then you pick this. But if you just want to measure it in the positive direction, the way we define the argument, then you can as well keep the anti-clockwise direction measure. And then once you are at this point, it's already 180, then you add this value of alpha. Then you look at the angle will turn out to be positive, more than 180 degrees. But when you restrict yourself from minus 180 to 180, that's why now you have to measure in the negative direction. And that's why we are giving the angle as a minus, or having a minus sign. So that is the third case. And then the other case is going to be, so let you not be confused that we are saying that if you restrict yourself to defining argument as principal argument, then the angle should be between minus pi to pi, or what we say minus 180 degrees to 180 degrees. And so when you are dealing with complex numbers in this quadrant, so if you say this is quadrant 1, this quadrant 2, this quadrant 3, and this quadrant 4, then when you are in quadrant 3, remember that if you have to remember that the direction which is positive is from this real positive axis going in the anti-clockwise direction. So if this is the motion you are picking, then all your angles will be positive. And so when you are in the third quadrant, if you have to measure the size of this angle, if you are to go to the positive direction, you see that you'll actually be surpassing the 180 degrees going past 180 degrees. So if you want to restrict your argument to be a principal argument, then it means that you'll not go with this direction once you're in the third quadrant. You need to reverse the direction so that the angle you get will be less than 180, but in the negative direction. So that's why we are going to, once you have the value of alpha using the tan inverse of y over x, then we simply negate the value after subtracting from 180. So that now we have the size of this angle here. But if you want to keep everything positive, once you get the value of alpha here, then just know that if you are to read all these sides of this angle is simply 180 plus the value of alpha here. And still all of those two angles, like in this case, if you define the tan of 236.31 and tan of minus 123.69, is exactly the same thing. So case 4, which is the last case, if your complex number is now in this fourth quadrant, if the number is here. So if the number is here, then you do the same thing. Make this an alpha. So you say this already changed in y, this actually along the x. So tan alpha is going to be opposite, which is y over x, which means that alpha is tan inverse of y over x. So then once you have the alpha, remember that since the reference is this real axis, and when you move in this direction, you have plus. When you move this direction, you have minus. This will have argument will give you a negative value. So what you get as alpha here after working out the tan inverse of y over x, you negate it. So maybe you can demonstrate that one with a real example. For example, we have the number z equals to 5 minus 2i. So what you should usually do, you sketch the number in an Argand diagram, and you know that if z is 5 minus 2i, it means that this number will be in this fourth quadrant. That along the x we have 5 units, along the y we have 2 units, and then in the negative direction. So this is what you call alpha. So tan alpha will be opposite, which is 2 over 5. So which means alpha is the same as tan inverse of 2 over 5. So 2 divided by 5, then you define its tan inverse, you get 21. So this will give you 21.80 degrees. If you want to convert into pi radians, you divide by 180, you get 0.1211 pi radians. So argument, if you want to restrict yourself from the range minus 180 to 180, then becomes negative of alpha, which will be negative of 21.80 degrees, or negative 0.1211 pi. That is a principal an angle that is measured between minus 180 to positive 180 degrees. But if you want to give your angle as a positive angle, then it means that now you'll be referring to this measure. The measure there will be this will be the measure. So that now it will be simply 360 minus the value of alpha, because the only thing that is remaining for us to get a full 360 degrees is this value of alpha. So this will be the same thing as writing 360 degrees minus 21.80 degrees. And this will give us 360 minus 21.80 to give us 300. So we can either give this or we can give this one. But know that when the question specifies that we need to find the principal argument, then the range is between minus 180 to positive 180. So you have to measure the angle in the reverse direction if you are dealing with complex numbers in the fourth quadrant. So that's what we need to always keep in mind. So note that a complex number exists in three different forms. So when we write z equals to x plus yi, the usual definition of a complex number, then usually this is described as the Cartesian form or the rectangular form. And then there's what we call polar form. And polar form is z is given by r into cos theta plus I sine theta. And there's what we call exponential form, which is z equals to r e raised power I theta. And in all these cases, r means the modulus of z, which is the square root of x squared plus y squared, and theta is the same as argument of z, which is defined according to lies, as we have described in previous cases on how to find argument of z. So let's give an example. So convert the following into polar and exponential form. Maybe just even before we do that problem, it's good actually to see how why we say that polar z can, if z is x plus yi, then this is also how it can be presented. So just as a recap or recall that if I have this as my imaginary axis, this as my real axis, and I have a complex number z here, x plus iy, in this quadrant, if this is my angle theta, then this height of this triangle will be y, this base will be x. So that from Oshachota, we can say the cos theta, cosine of this angle is adjacent of hypotenuse, so adjacent is x. Now make this, call it r, which is usually the same as the absolute value of z. So the same as x over r, which means r cos theta is the same as x. when you cross multiply. And then sine theta is the same as opposite, which is y, over hypotenuse, which is r, which means r sine theta is the same as y. And then because x and y are what define the complex number z, then tan theta from this triangle is opposite over adjacent. Opposite is y, adjacent is x. So this means theta alone is tan inverse of y over x. So z, which was written as x plus iy, will be the same as x value is the same as r cos theta from here. From what you've obtained here is the value of x, and then y is the same as r sine theta. So when you rearrange this one, we have r into cos theta plus I sine theta. So this is how z will be. So this is what we call the polar form. And then later on, we'll derive that e raised power I theta is the same as cosine of theta plus I sine of theta. This identity is called the Euler's identity. So we'll later on see how that identity is obtained. So e raised power I theta is always the same as cos theta plus I sine theta. So that's why now when we have z equals to r into cos theta plus I sine theta, we can write this one as r e raised power I theta by using Euler's identity. So this is what you call now, when you have complex number expressed in terms of t, in terms of exponential, then this is what we call the exponential form. While this one is what we call the polar form. So having that now, let's see how we can do the conversions from rectangular or Cartesian form into polar form. So change or convert into polar and exponential form. So the first one is z equals to minus root 3i minus I. So remember, there are only two things that you need to have in this case. One is to write the number or write z in terms of sine and cosine. And before you do that one, you need to know the angle theta in the definition. So solution, first find r, which is actually the modulus of z. And in this case, we'll have the square root of minus root 3 squared plus minus 1 squared, and the answer would be 2. Because we'll be having square root of 4 which is 2. Remember, the modulus or length or absolute value of z is given at the positive square root. Now, to know how you are going to define theta, you need to visualize in which quadrant does your complex number lies. So if these are minus, so it means that real axis is minus, then imaginary axis is also minus. So the number will be in this quadrant here. So this way will have minus root 3 minus I. So where minus I mean that along the vertical axis, there's one change, 1 unit, and then along the real axis, we have root 3 units. So find this alpha. So tan alpha is opposite, which is 1 over root 3. So alpha alone will be tan inverse of 1 over root 3. So 1 divided root 3, tan inverse of that value is 30 degrees, which you can convert in pi radians as 1 over 6 pi radians. Now, there are two ways of actually defining your theta. You can either decide to make it a positive angle, or you can, if you use this direction, then theta will be positive. But if you want the angle to restrict the angle to be between minus 180 to positive 180, then you use this direction, and this will be minus. So theta will be given by, if you take the positive direction, is simply 180 degrees plus 30 degrees, which is 210 degrees. This is the same as 210 divided by 180 is the same as 7 over 6 pi radians. But if you want the angle to be negative, still be accepted, you can write your theta is the same as, remember this should give us a total of 180, so it will be negative of 180 degrees minus 30 degrees. So negative 150 degrees, because this is 30, to make a complete 180, you need now 150. But then 150 measured in the negative direction. Or this is the same as 150 divided by 180, the same as 5 over 6 pi, but negative. So remember, whether you pick 210 degrees or minus 150 degrees, all of them correct values. Because when you define the tangents of those two angles, you get exactly the same thing. So you can either decide to restrict yourself in the positive direction, or you can decide to restrict yourself for alignment. All of them will be correct. So therefore, Z, which is usually written as R cos theta plus I sin theta, will be given by R. We have gotten the other is 2, and then cos theta is 7 pi over 6 plus I sin 7 pi over 6. So that is what will be the polar form of that given complex number. Or you can write it as 2 cos 210 degrees plus I sin 210 degrees. Or if you like, you can write it as 2 cos minus 5 pi over 6 plus I sin minus 5 pi over 6. You don't have to write all these forms, so I just stick to one. or you can write it as 2 into cos minus 150 degrees plus I sine minus 150 degrees. Then the exponential form is simply z equals to r e raised power I theta. So which will be 2 e raised power theta is 7 over 6 pi I. Or you can write it as 2 e raised power negative 5 pi over 6 I. All those two represent the same thing. Then another example. So remember the key thing that now when you are given a complex number form and they've been asked to find its polar form, you must always start by checking where the number lies. And once you have known where the complex number lies, then you'll be now in a position to express or to find the number to find the correct value of the argument and modulus, and then give the correct form. Another example, given the complex number z equals to 2 plus 7i, find modulus of z, and then 2 argument of z, then 3 polar form, and then 4 exponential form. Good. So remember the key thing is that the first part of finding the modulus of z is very obvious. It's positive square root of x squared plus y squared. So z is square root of 4 plus 49, which will be the square root of 53. Then argument, you can't find correct argument before sketching the number to know where the number lies. So always remember that argument depends on where the complex number lies. And this number, because x and y value are both positive, then it is in the first quadrant. So this way we'll have our z, which is 2 plus 7i. So which means that to get the argument is very direct, that theta is simply tan inverse of y is 7 units, x is 2 units. So we'll have tan inverse of 7 over 2. So tan inverse of 7 over 2 will give us 74. This theta is 74.05 degrees. When you divide by 180, you get this is the same as 0.4114 pi radians. So which means then now that argument of z for this problem will just be the same as theta because it's the complex number in the first quadrant. So it'll just be 0.4114 pi radians. So that is what we get there. So I remember when you want to write it now, the normal radians, you can actually say this is the same thing as saying 0.4114 times 22 over 7 radians. So which is the same as 1.29. Say 3 radians, but you don't have to do that. Just write in terms of pi. This is complete. This one is really not necessary. When you write pi, we still know that it means pi radians. So then now to write the polar form, so polar form is z equals to r into cos theta plus I sine theta. So which will be z equals to r is root 53 into cosine of 0.4114 pi plus I sine 0.4114 pi. Or if you like, you can say root 53 into cosine of the angle was 74.05 degrees plus I sine 74.05 degrees. Then the exponential form will be z equals to r e raised power I theta or theta I. So which will be z equals to root 53 e raised power 0.4114 pi I. Then same question to find the modulus, find the argument, and then express in polar exponential form. Z is given by -4 minus I. So we begin by modulus. So modulus of Z, which is also given as R, is the square root of -4 squared plus -1 squared, which is the square root of 17. Then argument cannot be found before sketching the complex number in the Argand diagram to know how you're going to interpret it. So minus minus means that this number is in this quadrant. Then you define, call this one alpha. So along the x will be 4 units, along the y will be 1 unit, or parallel to the vertical axis. So tan alpha is opposite 1 unit over adjacent, which is 4 units. So find of 1/4. So this will be given by alpha is the same as tan inverse of 1/4, which will give us the value is 14.04 degrees, which is the same thing as 0.07798 pi radians. So once we have that, then the next thing will be to find the accurate value of the argument. So remember the argument, you can either measure it in this way or this way. So if you have to measure it in the positive direction, then theta will be 180 degrees plus 14.04 degrees. Or you can say minus of 180 degrees minus 14.04 degrees. Because remember, this direction is negative while this other direction is positive. So here we'll have 180 plus 14.04, which will be 194.04 degrees. Or if you want to go in the reverse direction, will be 180 minus 14.04 minus, so it'll be negative 165.96 degrees. So now, having that, so you can as well now convert this into the pi radians. So simply dividing each of them by 180. So this is like this 1.078 pi radians. Or this one will give us negative 0.922 pi radians. So then now we write our Z is the same as R, which is square root of 17 into cos 1.078 pi plus I sine 1.078 pi. Please note that the same place we are putting 1.08 pi, you can put negative 0.922 pi, same thing. So this will be the polar form, while in the exponential form, we'll have Z equals to root 17 e raised power 1.078 pi I. So that is what that problem will give us. And then lastly, express Z equals to -1 minus I in polar and exponential form. Where theta lies between minus pi and pi. So solution, remember that polar form means Z equals to R into cos theta plus I sine theta, where R is the modulus of Z, and in this case we'll have -1 squared plus -1 squared, so which will be root of 2. Argument, which will give us the value of theta, can only be correctly obtained once you fetch the complex number to know in which quadrant the complex number lies. So having both the real part is negative and imaginary part negative, that number is in this quadrant. So this 1 unit to this 1 unit, call this one alpha. So tan alpha is the same as 1/1, which means alpha is the same as tan inverse of 1. And all of us know that tan inverse of 1 is 45 degrees. 45 degrees is the same as when you divide by 180, you get a quarter pi. And remember, we need argument is measured. There are two ways. You can either measure it following this direction, the angle will be positive. But remember, when you measure in this direction, the angle will be outside the range specified, -1 minus pi to pi. So what happens is that now we need to pick this as the direction of measure. So this is what is going to be the correct way of measuring theta. So the correct value of theta is going to be, remember, this is a negative direction. So we'll have minus. And then remember, this part plus this part should give us 180 or pi. So which means they are going to have pi minus this alpha, we have gotten it to be pi over 4. Or if you want to use degrees, then it'll be now 180 degrees minus 45 degrees. So this will give us negative. So pi minus pi over 4 will be minus 3 pi over 4. That will be the correct value of theta because the question has already specified the range where theta should be. But if the question was open, then remember that you can as well take the other positive direction as 180 plus 45 degrees. But because the question is specific that the value of theta must be between minus pi to pi, then this must be the direction that you need to pick. And remember that you'll be interested in this angle here, which should be simply 180 or pi minus what you have as alpha. But remember, the reference is always the positive real axis. When you move downwards, so values are negated. So that's why I have this negative here. So which means then that our z is going to be r, which is √2, into cosine of the theta is minus 3 over 4 pi plus I sine of minus 3 pi over 4. So that will be the polar form of that given complex number, while the exponential form will be √2 e raised to minus 3 pi over 4 I. So that's what we get in that given problem. So the main take home from this discussion is that you first have to understand how to represent complex number in an Argand diagram, which is simply the same way we plot points in the real axis, with the only difference that our y values are the complex values. And then when you want to find the argument of a complex number, always sketch the complex number in the complex plane to know how you are going to measure the angle with reference to the positive real axis. And remember that the way the values are measured from this positive real axis is that when we move in the anti-clockwise direction, when this is the way we are moving, it is always plus, but when we are moving this way, it's always negative. And when you restrict your argument to be a principal argument, then it means that your values must be between minus pi to positive pi. So you have always to remember to sketch and then see how you are going to read the values with respect to the real axis measure. Thank you.